Okay. Okay, everybody settle down, and we'll get started in a second. Okay. Welcome to lecture 19 of CSE 548, the analysis of algorithms. Let's start things off. First of all, are there any questions about logistics or any questions about homework before we get into the meat of the exam thing? The exam has been delayed till next Thursday, so nobody here should be expecting to take an exam. And the homework is due to Tuesday after break. Okay, any questions about the homework or? Wait, what was that you said about the homework? Homework is due, I believe, Tuesday after break? Yeah. Okay, yes. Okay, question? What were the results of the contest? I want to go through that now to start things off. First of all, the way the homework, the scores were graded were, we took an average of the largest sizes you could solve in a minute and took the logarithm of that. Okay, and then compared that to the logarithm of the largest anybody could do. So the largest anybody could do would get it to be 100. Okay, since your programs we were taking the log of that score. How does the log of, let's say, 30 compare to the log of 15? Okay, if you remember what the properties of logarithms are. Okay, not much of a difference. Remember that the difference, if you solve twice as large a problem, you only get one more in the logarithms. Okay, so the net result is that if your program ran very slow, okay, on the order of 8 to 10 vertices, you would still get 66% about of what the fastest program got. Okay, but anyway, let's go through with a contest. Okay, there were 11 competitors who had sort of submitted programs to me. Okay, and what I started to do was to run them on various files. They all ran on the smallest files. The first trouble came when I gave the grid graph GG20, the 20-31 file. Okay, and the programs that couldn't take that graph, the vertex GG20, the ones that couldn't take that were, okay, and there. So we were down by a couple. I think there may be a couple of others that had trouble with that. Yes. These programs couldn't take the grid graph 2020. So then we scaled things up a little bit to see who could take the grid graph GG25. Okay. And over here, the programs that couldn't take it were, okay, actually, he had died a little bit earlier. Okay, okay. This is actually a ringer from past years, so we'll delete that one. Okay. Then we tried the programs. I tried the random graph 20 vertices, and this died, this died, this died, and this died. Okay, so everybody was still sort of alive at this point. Okay, we beefed things up a little bit, and next tried the grid graph 30. Okay, and everybody could sort of take that. Okay, except that program. Okay, then we tried beefing it up a little bit more. Okay, up to 35. Okay. And here we started having a problem. Okay. This program gave a different answer than it should have gotten. Okay. So that one got eliminated from the competition. Okay. And now we were down to 2. Okay. And battled on this for a while. And tried, since they couldn't do the random graph 20, I had them work on the random graph 19. And they couldn't do it. Then we did the random graph 18, okay, and Ingmar could do it in 51 seconds, okay, where this program could not do it in 500 seconds, okay. So the ultimate winner, okay, is Ingmar, okay, And the undergraduate winner is Vlad. So please come up here. We have the graduate and undergraduate winners. Round of applause. Okay. So here we have, for each one of them, they'll get rewarded with a copy of my book, okay? And it's signed, okay, to the leader of the bandwidth, okay? My congratulations, okay? Here's the graduate winner, which is Ingmar, and the undergraduate winner is Dario. Round of applause. But before we let them go, how did you do it? Explain to us how you did it. Okay, let's start. Maybe we'll start up here. Tell them what your algorithms were.
Okay, I made sure I had a good starting solution. Before I actually do the researching, I just find out I got the minimum starting bandwidth by using just random swapping of vertices. So once I have a good small bandwidth, then I start a search. And by doing that, I could eliminate a lot of branches in a tree that would have been searched otherwise, so it saved a lot of time.
Okay. Okay. Well, okay. Empty paper. Okay. Yes. Here. So how did you do it? I got a.
Yeah, well, I also started trying with a very good first shot, and that meant a very easy one is you just pick one vertex, and to whatever he is connected, you put that. And if he's connected to 3 guys, you put those in the next 3 entries in your permutation array. And then you take this one, and he's maybe connected to these 3. This one was already taken, fine, and then put those 2. And from here, whatever is not yet taken care of, you put it next, and so on. So it's kind of you have this graph lying in a box, you pick a vertex and pull it up, and they naturally fall down. And you do that with each vertex. Bandwidth as your starting point. And that was O of n algorithm to do this first try. And I did that n times, so it's n squared, what I used to find my best permutation. And then after I had that, I also thought, okay, if my best shot has a bandwidth of 10, then I'm going to take the first 10 elements and I'm going to run all possible permutations of those 10 elements just within those 10. Improvement fine, and then I switch my window one more and do it with all those 10 in there and all those 10 in the next one. And that normally cut down the bandwidth by another 1 or 2, which would mean you had one local edge which was too long, and you could cut it. If you had 2 long ones somewhere separated, you could not hit that. And after that, I started the normal pruning, and I had always a pointer to my maximum and to the current maximum bandwidth, which was the best one I found so far, and the minimum. And you can at least say something if your maximum degree plus 1 over 2 is something what is a lower bound to your bandwidth. I mean, they have to, the best one would be you have half of them to the left and half of them to the right of that vertex with the highest degree. So whenever you reach a solution which is equal to the optimum, you can stop right away. You don't have to do any more stuff. So that helped. And if I found out that some solution is not, I don't know, if I started in an array having placed these vertices and then there were empty ones left, to find what is the theoretical minimum possible for this beginning here, I checked which were completely fixed, and I took the maximum out of those. And then I checked, okay, this vertex here has an edge to the left of bandwidth 3, but he has also 4 other adjacent guys of whom I don't know where they're going to be placed. If I assume the best possible outcome, they're going to be in the next 4 spots. So out of the non-placed ones, it's 4 extra.
So what you're saying here, pruning idea, is what I'm thinking you're saying. You mean out of here, you have some other, okay, is it out of here?
It doesn't, okay, maybe even this one.
Okay,
if
this one here still had some degree, some vertices that hadn't been placed.
Right.
The bandwidth for this layout had to be at least out to here.
Right.
Without actually placing these ones.
Yeah.
Okay? And so we could do the cutoff based on the partial permutation length plus the number, the unmatched degree, or 1 minus the unmatched degree from here, 2 minus from here. And so we could prune faster without actually having to put down the partial permutation.
Correct. And
Okay? That is probably the winning idea here.
And I had an adjacency list of those vertices, so I only had to check those edges which were actually innocent with one of those vertices. So at the beginning, I mean, at the very first thing, I just ran through all edges, which always was only a very small fraction of the edges which I'm actually testing.
Okay, very good.
Yeah, and then once you find out that this possible minimum bandwidth is the same to what you've already found, then you discard all those later on permutations and change this one.
Very good. Okay, thank you very much. Another applause for our champions. Okay. Now, just on the contest. Oh, first of all, we also said we were going to award prize to the slowest program. Okay, and the slowest programs crapped out at around 7 or 8 vertices. Okay, and to encourage your programs running faster. Okay, anyone who has a program that slow can come to me and claim some XLAX, which I will give to the winner so that their programs run faster. Okay, and if you don't know what that means, go to a drugstore and find out what XLAX does. Okay, any other questions? Okay, so what were the lessons that one should have come out with here? First of all, as I would have predicted in advance, okay, the difference between the fastest and the slowest programs, or the fastest and the average programs even, was humongous. Okay, I mean, it was clearly much different than the performance between doing it in a supercomputer or doing the algorithm by hand even. Okay, I mean, we had the fastest ones were capable of routinely doing 20 to 30 vertices. The others stopped on a dime about 8 or 9, and it got 10 times, at least 10 times harder each time you added one other vertex. So we're talking about a program that by the time you got up to 20 vertices would have been 10 to the 10th times as slow. Okay, we're taking that much more time. Clearly, much big difference. Here's an example where the algorithm clearly would have had a better impact on the hardware, bigger impact than the hardware. A second take-home lesson is that different algorithms perform differently on different data. Some had an easier time with the random data than the others. Some had an easier time with the grid graphs than the others. Okay? Lessons from this are, first of all, that if you really have a program and you want to see exactly how it's going to do, it does pay to do some experiments. But the bigger lesson here is that sometimes if you know something about your data, okay, you could design an algorithm that might be better for that particular kind of data. If you knew you wanted to work on sparse graphs, okay, there'd be a different kind of algorithm there that you might be able to look at. Okay? None of the programs could efficiently go far beyond, let's say, 30 or so. Okay? I mean, on the grid graphs, some could go faster, but they all crapped out around 20 on the random graphs. Okay? Nobody came up with a polynomial time algorithm for solving this. Break. Okay? The interesting thing is that many of the fastest programs were very, very short and quite simple. Okay? I know that, as I remember looking, Dario's program came in at about 240 lines. Okay? And that probably includes comments and headers and things like that. How long was yours, Ingmar? This, I think, is a big one. But how long was your program?
Files and I don't know. It looks big, but the actual part which does the real computation was 3 pages on the screen.
Okay, so then the heart of it was 3 pages. Okay, the whole thing was big, but for various reasons, which presumably aren't that important. But the important thing was that there were programs, like, let's say, Dario's program, which came in very short, very clean. And that's really what is important here. Okay? speed up their program by adding a lot of complicated tests. Is it a path? Okay, if it's a path, do better. Okay? Well, many of these enhancements probably slowed the program down because they were making extra tests of things that really weren't why the program was spending a lot of time in the first place. Okay? And, so again, to keep it simple. Now, what were the winning optimizations? Again, we heard from the champions themselves. But basically, both of them were finding a good initial solution. What were you trying to do? You were trying to find the best possible permutation. If you knew which the best possible permutation was in advance, you were better off searching for it. Okay? Because really, most of your time spent in the program is proving that there isn't a better solution than once you've stumbled upon the best. Okay? So in order to help that and help find a solution, people use different things to try to find good initial solutions. Some used randomization. Okay? Some used, we heard Ingmar talk about some kind of an idea of doing basically a breadth-first search from each vertex, okay, and maybe monkeying around a little bit with it in order to come up with a good solution. Finding a good initial start was a big win, okay? Similarly, to help constrain the search, okay, using the fact that if you have a vertex of degree, let's say 5, you knew that no matter how you would lay this thing out, okay, there would have to be some edge. Let's say a vertex of degree 6. If you had a vertex of degree 6 in the graph, you knew that no matter how you laid out the edges around it, you had to have an edge of at least 3, okay, because there had to be at least half the edges on one side or another, and there's no place to stick it. So half the degree of the vertex was a good lower bound on anything. So hopefully, if ideally they had found their solution and this matching lower bound, they could have stopped immediately. Okay? But if not, it constrained things. Okay? The big win in searching was to make sure that you did some pruning. And the basic idea in doing the pruning, okay, was to make sure that the moment you had in a partial solution, the partial permutation you put down, the moment you had an edge that was greater than or equal to the target, then you could stop that subpermutation and back. Okay? Is there anybody who doesn't see what I mean by this? Okay? Question? Okay. So what was the idea? The idea basically was, suppose you put down vertices A, B, and C. Suppose you knew that the optimal solution, you had a solution, okay, of involving 3 vertices. Okay? A solution of the graph. Maybe the graph had 50 vertices. But you had a solution where the best bandwidth on your solution was. Suppose when you put down a partial permutation, you already had an edge here whose length was 3. No matter what you did with the rest of the vertices, okay, if you're putting down the vertices to the right of that, that's not going to shrink this edge. There's no way the bandwidth for any permutation that started with this could possibly be shorter than 3. And if you already had a complete solution of 3, you could backtrack immediately from here. Okay? The big win between the very slow programs and the contenders. This is what it took to become a contender. Okay, was to prune things out and do that in a proper way. Okay? In order to be a winner, okay, you had to do something a little bit cleverer. Okay? And one idea Ingmar said was not only did he keep track of what's the longest, the best solution so far, the longest edge, something about edges that hadn't been placed yet. Because he knew that if there was a vertex here of higher degree, those edges had to go someplace. And this ability to look ahead is probably what it took to get him to the next level. Okay, that I think is probably the solution there. Okay? Any questions? One idea which I would have liked to see somebody try, which did not, which I think would have been a big winner, okay, would have been the following up. Putting in the vertices from left to right. Suppose you know that the minimum bandwidth, you have a bandwidth solution of 3. So in order to beat you, you've got to make sure that there's got to be a solution that is, everything edge has to be less than or equal to 3. Suppose that you put the first vertex down here, okay, that you placed by backtracking. Where should the second vertex be placed? The second vertex immediately to the left. You could skip 3 spots and put this as the second position for the vertex you place. So what am I saying now? You're building up your solution, A, B. Instead of thinking AB is going leftmost, next leftmost, why not put A here and B here? What's the advantage of that? If there is an edge from A to B, you automatically get a cutoff, okay? Because you know that any edge that you've created the long edges first. If you're putting things in from left to right, really what you're doing is you're creating small edges first. And your goal to try to prune this thing is to prune it as fast as possible. So by either spacing the vertices out or alternate, by your base, or putting them alternating left, right, left, right, left, right, which is a weaker form of this, you would be placing down edges quickly that were likely to be long. And if they were long, you could immediately backtrack. Okay? And so this, I claim, could have done better. Yes?
What if there isn't an edge between A and B?
Then,
There is an edge between an A and B.
if there isn't an edge between A and B, you're perfectly fine to put them there. Now you put down C. Where should C go? Backtrack then, if there was no edge between A and B. Okay? But now you would put down your next vertex. Let's say C here. If there was an edge between C and B or A and B, you would immediately backtrack. Okay? And so my claim is that by being, by changing a little bit the order in which you're sticking these things in, you could actually have forced yourself to get cutoffs a little bit early. Okay? How many people see what I mean by that? Okay, and agree? Okay, how many people don't see it? Okay? Again, the important point being there was nothing magical about putting the vertices in from left to right. Every permutation could be described by a permutation from left to right. But there's no reason why, instead of putting the vertices left to right, we couldn't have had other positions to assign each slot to. Okay? And let that be the one. Yeah?
I had one very similar idea for a very good heuristic at the beginning, but I had no time to. If you start with the vertex with the lowest degree,
right,
and then check out of those he is adjacent to which one has the highest degree, and then say, okay, most likely that one should be as far away as possible from the first one you picked.
Right.
So you go on degree over 2 away
Okay.
from the first one, and then you try to deal with those adjacent to that one with the highest degree.
Okay. So sorry.
Yeah, and that gives something similar.
Okay. So again, other heuristics like this are reasonable. Yes.
I don't understand how you even show it, but you still, how do you implement that?
Well, what am I doing here? Okay, again, I can see where this is a little tricky, but let's think what I would have tried. Okay? You agree that you're building up a partial solution. Let's think of it this way. Here is a partial solution that you're building, right? Vertex A, vertex B, vertex C. This is what you guys did, right? What about if we had a that mapped each one of these elements to a different spot on the array? Okay? So any permutation of this is really describing a different layout. It's a well-defined layout because there's a one-to-one mapping between every permutation and permutation here.
Well, how would you figure something like that out?
I mean, how would you have figured out that? First question is, do you believe that this is correct? Okay, it's got to be correct because I'm going through every permutation here, because I'm doing the same thing to it, every permutation. I'm not erasing any permutation. I'm just scrambling it up in the same way. It's like instead of reading all permutations from left to right, it would be the same as if you read them from right to left.
Oh, I see. Different position.
Right, so I'm just taking this thing and automatically defining a different position, permutation. But since every one of these is mapped uniquely to one of those, going through all of these is the same as going through all of those. The advantage, though, is that I'm going to get a bigger cutoff here because I'm getting a big edge. Okay? Because somehow, instead of when you put the first two, you won't get a big cutoff. You might get a big cutoff if you. Okay? So this is the idea that I think would work a little bit better. Okay? How much better? Since I haven't run it, I can't guarantee you. Okay? But it's just another idea that I think would have some hope. Yeah.
And there was one other thing. Whenever you have to compute the next permutation, that was not obviously trivial. I mean, if you just have a set of next possible ones, then it's kind of an O of n.
Okay, so the question about how do you speed up finding the next permutation, probably affect your program by a constant factor, but that's not going to really change the search.
The idea I had was O of n, and then I got it in constant time.
Okay, so that might save a factor of n, which might be 20 or 30.
That's
But the big wins come in doing the searching. Okay, and that's really what we tried to do here.
Yeah.
Okay, any questions? Yes. What I'm trying to do is say this thing. Any permutation, we're right now trying to prove that there is no, in your search basically, what's the heart of your search? You find a current best one. You have a current best idea of what the backtrack is. You're then going to be searching to try to prove that that really is the best. Okay? If it really is the best, everybody else is going to fail. Okay? To be shorter than that. So your goal is to try to help it, make them fail as quickly as possible. Okay? The advantage of scrambling it up like this is that if, let's say, the optimal bandwidth was 7, if the optimal bandwidth was 7, you would have had to put down 7 vertices before you had any possibility of doing any pruning. Correct? Okay? Because there's no way you're going to get an edge longer than 7 until you put down all 7 of them. Okay? With my pruning much quicker. Okay? And so, so if there are edges there to be created, I'm gonna, if there are longer edges being created, I will identify those long edges faster than you would. Okay, is my claim. Again, you can't, if Ingmar wants to challenge me and say I'm faster than that anyway, I can't argue, because he has a program and I don't. Okay, but the important idea here, in fact, it is by no means trying to steal anybody's thunder. Here is that we're trying to do quick pruning. And Ingmar did that basically. Ingmar got the same effect a lot of what I did by this look-ahead scheme. By noticing that once he put down a set of vertices, he could in fact prune from beyond it. Okay? And that enabled him to do pruning faster than putting down just all those vertices. That's sort of the hope that he was trying to do, and that was a successful thing. Any questions? Yeah.
How did this semester compare?
Okay, the winning program here was faster than the winning program from the previous time. Okay? The previous time was an undergraduate-only class. Okay, but the winning program here was the faster than the other ones.
Was the winning undergrad this year faster than the
I don't remember. I think it's probably comparable-ish. I think this may have been a little faster, but comparable. Okay? Any other questions? Okay, I hope this was an instructive thing, and I hope people enjoyed it. I know some people did not enjoy it, but hopefully some people did. Okay, let's move back to sort of what we were talking about last class. We were talking about spanning trees and minimum spanning trees. I'd like to go through the problem of the day. Question.
One more thing.
Yes.
The winning program was recursive all over, so I didn't.
So your program was recursive.
And it was in C++, so it was most high-level possible.
Language independent, right. This language didn't make much difference. The recursion didn't make a difference. The difference was how far ahead did you look to prune. That was the big win. That's the moral here in doing backtracking. Okay? Any questions? Okay. What about the problem of the day? Okay? The problem of the day asks, we were talking about spanning trees, describe an efficient algorithm that, given an undirected graph, determines the spanning tree of G whose largest edge weight is overall spanning trees. Now remember, minimum spanning tree, what we were looking for was a spanning tree that minimized the sum of the edges. Here what it's asking for is find the spanning tree that minimizes the length of the maximum edge. Okay? So here we don't care how much total wire we use, so long as we don't use any to connect all the homes, so long as we don't use a big piece. Okay? And the question is, try to find a tree that's going to do this. Okay? Does everybody see the difference in the that we're using? Okay? So what did we do here? Yeah, again, the way that we would verify that is we would construct some examples. Here we've got a tree where the maximum edge weight is 5, although there's a lot of 5s. Here we've got a maximum edge weight of 6 and a lot of 1s. Although the sum of this thing is less, okay, this thing would be, in fact, better as far as the max length, minimizing the maximum length, even though this would be better minimizing the maximum difference. Okay? Now, when I started thinking about this problem, I said, okay, you want to minimize the maximum length. Doesn't Kruskal's algorithm sort of do something like that? What did Kruskal's algorithm do? Remember, it sorted the tree edges from smallest to largest and added the edges in from smallest to largest, okay, and stopped the moment it had a spanning tree. That was what Kruskal's algorithm did, okay? And if you ask me, that's exactly what we want to do here. If we think about it, if we start adding edges from smallest to largest, okay, and stop the moment we add an edge, the first edge, an edge that makes us to have a spanning tree. My claim is that has to be the spanning tree that minimizes the maximum edge. Why? Because you didn't have a spanning tree until you'd added that edge. Okay? And you added all the smaller cost edges. So it should be clear that if you sort the edges by order of increasing weight and stop the instant that the edges that you've added form a connected graph, this will minimize the maximum edge weight. Okay? How many people believe that? Okay, that seems pretty obvious. But what's interesting, wait a second. Okay, if Kruskal's algorithm does that, and Kruskal's algorithm always finds the minimum spanning tree, that says one thing that's a property of minimum spanning trees. Any minimum spanning tree maximizes, is the one that minimizes the size of the maximum edge. Okay? They're not really two different problems. In fact, the tree that does this, or any minimum spanning tree, does this. The tree that does this is a minimum spanning tree. Okay? Because it is possible, let's say, that you could have a situation where the one that minimizes the minimum spanning tree could look like this, all 1s and a 2. And you could have another tree that has all edge weights of 2. This would have the same minimizing, it would sort of still have the same maximum edge, but the total weight would be different. But my claim is that the algorithm finds a tree that does what we want. Okay? And similarly then, Prim's algorithm, which also finds a minimum spanning tree, has to do the same thing. Okay? So in fact, both of these will actually give us a tree that does what we want. Okay? And the proof of correctness would be pretty much, sort of simple. Okay? Suppose it didn't, okay, give me a minimum spanning tree. Consider the edge with largest weight in it. If I delete it, that means I'm going to have a spanning tree here and a spanning tree here. If this was the largest weight, okay, in my spanning tree, if I delete it, I've got two separate spanning trees. If there was another edge that spanned these two that was less than max, then we know that Kruskal's algorithm would have picked that beforehand. Okay, and then this would not have been. Okay? So my claim is that this tree, Kruskal's algorithm will find this tree as well. Any questions about that? Okay? That should be convincing. Okay. Any questions? Okay, so where were we last class? Last class we were talking about minimum spanning trees. We had talked about Kruskal's algorithm. Kruskal's algorithm came down to the following. I mean, if we looked at what Kruskal's algorithm was, okay, I mean, it's maybe the paper's a little bit beaten up by now after the lecture. But the basic algorithm for Kruskal's algorithm was this, okay? We wanted to keep pulling out, sort the edges, pull them out in order from smallest to largest, and for each edge, test whether or not it created a cycle when we added it to the tree. How are we going to perform that test quickly? The claim was that we could do it as follows, okay? Every edge we consider, we find out what's the name of the spanning tree, the component, connected component containing vertex u, and find out what the name is of the connected component spanning v. If the names of them were different, that meant they were in different connected components. If they were in different connected components, adding this edge would not create a cycle. It would just create a larger connected component. Okay? Once we added it, the claim was then we had to sort of merge these two connected components into one component. Okay? And so what I claim is that if we can do these two operations, testing whether the two vertices lie in the same connected component, and later taking two connected components and merging them, if we could do both of these in log n time, this would give us an algorithm that ran in order m log m time. Because for each edge, we're going to be doing each one of these operations, which takes log time. Any questions about that, or is that clear? Okay? Very good. So how are we going to do those tests? Okay, the bottom line is that the minimum spanning tree algorithm is going to be fast if, okay, we can find a way to do those tests. My claim is we're going to be building a data structure. We need a data structure that will quickly be able to do two different kinds of operations, union and find. Okay? Union would be the effect of taking, if we have a data structure where we have n elements in our set, if we're allowed to maintain a set of subsets on that. Union will merge two subsets. Find will determine the name of our subsets. Okay? So suppose, let's say we originally have the numbers 1 through 7 in our subsets. We could talk about, let's say, merging, doing a union to maybe merge those two together, a union to merge these two together, and we then do a find. Okay, let's say we had merged these two together to make one subset. We merged this together. These are now all one subset. When we do a find, we'd like to be able to ask ourselves, if we do a find on 1, that's going to tell us the name of the subset containing 1. And we do a find on 2, it'll tell us what's the name of the subset containing 2. In this case, they're in different subsets. They should have different names. Okay? What are we going to try to do? My claim is that if we can support find and union operations, okay, we can do these connected components testing quickly. Okay? And right now I can tell I'm maybe being a little bit confusing. This is not that hard. This is something that you will see if you concentrate a little bit. Okay? How do we test whether two vertices are in the same connected component? Well, for the first vertex, we find what's the name of the subset that contains it. For the second, we find the name of the subset that contains it. Ask if it's the same subset. If they're in the same subset, then they're the same connected component. If not, they're not in the same one. As far as how are we going to be making two subsets equal, if we find the name of both of them, okay, find the name of the subset that contains this one, find the name of the subset that contains that one. The union operation, okay, is going to make one subset out of both of those elements, okay? And so that will make them the same, okay? Any questions? I can tell this is, I don't feel I've explained this very well. How many people are confused? Okay, a lot of people. Okay, let me try one more time. This, I think, is my fault. Okay? My claim is we're going to have the following kind of a data structure. Okay? Originally, we've got a bunch of elements, each of which is in their own set. Each one of these is going to correspond to a vertex in the graph. We're going to be allowed to do two different kinds of operations, one of which is going to be to merge two of them. So if I say, give me a union of 1 and 2, that's going to put them in the same subset. Okay? And further, give that subset a name. Initially, each element is in its own subset. We might as well say the subset that contains 6 is named 6. And the subset that contains 3 is named 3. Okay? That scheme breaks down the moment you have two subsets, or starts to have problems when you have two elements in the same subset. Which element should we name this subset after? Okay? You say the smallest. I say it doesn't really matter. Okay? So long as we give it a name and that everybody knows what the name is. Doesn't matter who the leader is, so long as everybody knows who the leader is. So what we're going to do is take the two elements when we do a union, is merge them and make one of them the leader. That leader is going to be the name of the subset. So if we do the union, maybe 2 is going to be the name of this subset. When we do a find operation is going to return who is the leader, okay, of that subset. If we did a find 3, who's the leader of element 3? 3, okay? If we do a find 2, who's the leader of 2? If we do a find 1, who's the leader of 1? 2. So if we can give each cluster its own name, okay, then my claim is we can do the connectivity testing. Okay? Because the moment we decide that two vertices are in the same connected component, we're simply going to do a union, okay, and merge them together and assign that cluster some kind of a name. Okay? So long as all the vertices know what their names are, okay, we're okay. Any questions? Question.
If you have union 1, 2, and I want union 2 and 3, what happens?
Okay? What's the situation? We have elements, the way I like to think about drawing these things, the leader should be the one on top. Okay, that's what the definition of a leader is. Why don't we represent these subsets instead by sort of trees? Okay? This is supposed to be an arrow. Okay? So 2 is the leader of this subset. Okay? I can take it back. Let's have everybody point to the leader. Okay? If you want to ask what's the leader of 1, well, leader of 1 points to 2, so it knows that the leader of 1 is going to be 2. None of these have pointers coming out of them, or their pointers could point to themselves. So my claim is by following a pointer, we can figure out what the leader of each element is. Okay? What's interesting about this? Okay? If we want to now ask ourselves, how do we merge 2 and 3? One of them is going to be assigned to be the leader. Which one? Well, for correctness, it doesn't really matter. We could make 3 the leader, which would give us a tree that looks something like this. 2 is the leader of 1, okay? 3 is the leader of 2. How could we figure out the name of the subset element 1 belongs to? Okay? What is the subset's name, the ultimate leader of the subset? 3. And how do we do that? By simply following all the pointers up to the top. Okay? What I'm proposing is a scheme by which we can maintain these subsets. Okay? Each element in your subset, each vertex, is going to contain a pointer to its immediate leader. Initially, 1 has no leader, so that's nil. In the original state, none of them have leaders, so all of these are nil, or each of them are actually singleton elements. Slowly, we're adding more elements. We're merging these subsets together. Whenever we decide to do a merge, what we're going to do is if we decide to merge, okay, the subset named 5 with the subset named 3, we are simply going to take the leader of this subset, 5, and have that point to the leader of the name whose it's going to inherit. By doing this tree step, this tree processing, we know that any name that we had here, okay, anything that had 5 as a leader, if we walk towards the root, now its root is no longer going to be 5, it's going to be 3. Its new leader is going to be the set that it was merged with. Okay? And by doing this kind of a walking scheme, we can maintain the correctness of these subsets. Okay? How many people are questions? Yeah.
Yeah, basically, the tree maintained is skewed.
Right. So what is the problem that we now have? Okay? We are now going to be starting out with these singleton elements and gradually doing merge operations. Each merge operation sticks this guy under somebody else. Okay? And another merge operation, okay, may do this. Ultimately, if I want to merge this subset with this subset and make this guy the leader, what do I have to do? Okay, if I want this guy to be the ultimate leader for all of these elements, which pointer do I have to change? Okay? If I change this pointer to go to here, would that merge the two sets together? No, why not? Because this guy, okay, does not know that he's been merged. If instead we merge the leader of this other subset, have that point to the leader of the original subset, now we've succeeded in merging everything. Why? Because every element here, and you ask him who its leader is, bop, bop, that's the leader. Every element here, who's its leader, bop, bop. There's only one root into the tree. Okay? That defines the leader, and that defines the name of the tree. Okay? Any questions? Okay? I feel I'm making this more confusing than I should, so don't be afraid to ask questions. Okay? The thing that's different about this trees than any other trees that we've built, these are trees from children to parents, rather than parents to children. Okay? That's the first thing to notice about these trees. Okay? Basically, we want to be able to ask ourselves, after doing merge operations, who's our ultimate parent? And since all the nodes in the tree have an same ultimate parent, the ultimate parent defines the name of the set. Okay? Further, it should be clear that when you have two separate trees, just changing the ancestor of one of the parent of the absolute ancestor of one of the trees to point to the ancestor of the other is enough to merge the set, because now they have the same ultimate parents. Okay? Any questions? How many people feel they see why the scheme is correct? Okay, how many people do not see? Okay, everybody claims it's correct. But there is a problem here, okay, which was mentioned a minute ago. These trees could get to be fairly lopsided. Okay? Suppose, let's say, we decided to try to merge this element with that element, and then this element with that element, this element with that element, this element with that element. The process of this guy finding out what its name is involves going all the way up to the parent, okay, up to the ultimate ancestor of the tree, the root of the tree. What is the time it takes for a node to find out what its root is? Okay, its time is O of n, or time is proportional to its height in this tree. Okay? If our trees could get arbitrarily skewed, it could take linear time for anybody to find out what their name is. Okay? And if it takes linear time to find out what time their name is, okay, since the process of testing whether an edge is going to create a cycle involves finding somebody's name, finding somebody else's name, if each of them takes linear time, the total time is going to be linear to do that. That is no better than if we had done a brute force search. Okay? If we're going to be able to use this data structure efficiently, we have to find some way to balance the tree. Okay? Any questions about that? What is the best possible height we could hope for in a tree with n nodes in it? Log n? Well, is that true? Is this possible? To have n different nodes all pointing directly to the root? Sure. Why is it possible? What's different with a binary tree? With a binary tree, we say we can only have 2 children. That's where the log comes from. Here we're saying we can only have 1 parent. Okay? Now, everybody here has, well, let's say one mother. Okay? It's sort of like saying if you have 1 mother, how many brothers can you have? Well, you can have a lot of them. Okay? There's no upper limit. And here, having a lot of brothers is a good thing. Why? Because suppose you had a flat tree where everybody was an immediate descendant of the root. How much time would it take to find out who your parent is? Constant time. Just immediately bop up to the parent. Okay? So realize what we want here is a flat tree. Okay? Ideally constant height, but certainly better than linear. Okay? We need better than linear in order to get what we want. Agreed? Okay. That said, okay, if we're not careful about how we do our unions, okay, how we decide to merge things, it could turn out to be linear. Okay? Again, one way that I would show it is, suppose we had to do a sequence of unions and finds. The first things we did were all unions, unioning each element to its predecessor to create one long path of n elements. That could certainly be done if we just sort of arbitrarily pick which one do we make the root when we do a merge. If we then did a find from here, each find, the unions would take constant time to do. Because all we're doing with a union, okay, is basically changing one pointer. The problem with having a skewed tree is that the find operations become expensive, okay? Because the find operations are what actually do the walking, okay? So what are we going to want to do? We want to find a way that we can decide when we've got 2 nodes that we want to merge. Here's a tree and here's a tree. We want to do a union of these. One of them is going to be made a parent, and one of them is going to be made a child. Which would be the better one to make a parent? Okay? You've got 2 trees, you're going to merge them. Which one would be better off making be the parent? Okay?
The one which has already the longest path to one of its children.
Okay? Suppose we have a case where this tree has a height of 7, and this tree has a height of 3. There's a root here, there's a root here. Which one would be better off making the root? Okay, 7. Why is that? Because when we link that guy in, what's the height of the longest path here now? Still 7. It hasn't changed. What's the height of the longest path from here down to here? Okay, it was 3. Now we add another layer of management. Okay, it becomes 4. So if we think about how we'd want to do the merging, the idea that should be the case is if for each tree we knew how tall it was, we could always guarantee that we would be making the right decision. Okay? Any questions about that? Okay? Now, the trouble is, okay, it turns out to be a little bit hard to keep track for every node. What's the height of the tree? Okay? Why is that? Suppose, let's just think for a second. Why is it that if we do merges, okay, keeping track of the height of the tree is a problem? Okay? Actually, there is no problem if all we're going to be doing is merges. Okay? Because we know that if we have a tree of height 7 and a tree of height 7, okay, what is going to be the result of merging it? How tall will the tree be? 8. Because one of them will become an ancestor. So my claim is that if we keep track of the height of each tree, just the height, okay, we could figure out which is the right guy to merge. Okay? Any questions about that? If we do that, how tall a tree will we end up getting? What's the worst case tree we could possibly get over any sequence of unions? Okay? Knowing the heights of these things. Okay? Let's think about it. When would we get into trouble, okay, doing merges? Yeah.
Both parts are the same.
Right. Suppose we end up starting out with a bunch of singleton nodes. And I say, make this guy be an ancestor of that. And make this guy be an ancestor of that. Okay? What's the height of this thing going to be? Okay, this is 1, this is 1. What happens when we now merge these things? Okay? What's going to be created? A node of size 3. A tree of height that's shaped like this, right? Suppose I did another thing of the same structure. Okay? I had done another set of merges. This was 3 merges that it took to create that. Suppose I did another set of 3 merges, and now did the union of this. What's going to be the happening here? Okay? The height has grown by 1, correct? Suppose I now did the same thing again. This would be the worst possible case. Okay? And I created another one of these. And now I ask to do a merge here. What's going to happen? Okay? What's going to happen to the height? It's going to increase by 1 again. If I have n nodes, what's the height of my tree going to be after I've done this operation? Log n. Why is that?
Because each time you double the number of nodes, you have 1 extra.
Exactly. Okay, if you think about what I'm doing here, okay, by using this height heuristic, okay, my tree might, in the worst case, okay, end up becoming the log, might clearly become of height log n by using this scheme, this series of unions. Okay? And why is that? Because every time I do this, I'm doubling the number of nodes in order to get 1 extra height. Okay? My claim is that by doing this, this shows that in fact the result of n unions might have a height of log n. How do I know that it won't necessarily be worse than log n? Okay? Okay? Basically, the proof is going to follow from the same kind of an idea. Okay? That if it's sort of, I would have to prove this in somehow kind of an inductive manner. Okay? The heart of this proof is going to rely on the fact that in order to go from a height of h to a height of h plus 1, okay, it means that it's going to have to double the number of nodes. Okay? If I can show that going from doubles the number of nodes, okay, then that would prove that there has to be a log n height, okay, in the worst case. Okay? And that, in fact, is the case. Okay? That if you were to keep track of the heights of each tree, okay, you would never do worse than log n. Okay? Any questions about that? Okay. How many people are sort of convinced? Okay. How many people are not convinced? Okay. I didn't give you a proof. Let me give what you should be convinced of is that if you merge by height, you should be convinced that the height can be as bad as log n. Okay? You haven't been really convinced that the height can't be worse than log n. Let me give you a proof that a slightly different merging strategy can never be worse than log n. Okay? What if instead of merging by by the height, we merge by the number of nodes in the subtree? Okay? So suppose instead of taking a tree and keeping count of what its height is, suppose for each tree we kept count of how many nodes were in it. Okay? This would be a simpler thing to do. How many nodes are there if we have a tree that has 5 nodes and a tree that has 7 nodes? When we do a union, how many nodes will be in the resulting subtree? Okay? 12. 5 plus 7. Okay? So my claim is we could keep track of the quantity of nodes in a tree just as easily as we could keep track of the height. Okay? Does everybody agree with that? Okay? My claim is if we keep track of the height of the number of nodes in the tree, we can prove that in no sequence of merges will there be a tree with more than log n nodes, log n in height. How do we prove it? We can prove it by induction. Okay? Okay? If you have a tree, okay, of height 0, we'll do an induction on the number of nodes in the tree. If the tree has 1 node, its height is 0. And the log of 1 is going to be 0. So that proves the basis case of the induction. In general, let's assume that this is true for up to n minus 1 nodes. Meaning that any tree that we build, by always putting the bigger guy on the tree with more nodes is the root. Let's hope that any tree that we build on at most up to n minus 1 nodes has height at most a log of that. Let's now think of what happens when we do a merge, okay, that will bring us up to n nodes. Okay? We've got a merge of 2 trees. The first tree, okay, tree 1 has height d1, tree 2 has height d2. When we do a merge, we're going to put the one with more nodes as the root. Okay? If we do this, what do we now know? There's 2 possibilities. Maybe the taller tree, or it may not be the taller tree. If it is the taller tree, then the height as a result of the merge is going to be unchanged. Correct? If you stick a short guy, okay, underneath after a tall guy, okay, the short guy will get worse, but it will not become bigger than the taller guy. So if in fact the tree nodes, more nodes, happen to be the taller one, the height goes unchanged as a result of the merge. And since the merge was of smaller trees, if the smaller trees satisfied our assumption, if the height didn't get changed, the bigger tree also has to satisfy the height assumption. So in this case, everything is fine. Okay? Any questions about that? If not, what might have happened? What might have happened is that, in fact, the tree that had more nodes may have, in fact, been shorter than the other one. But what do we know? After the merge, the height of the resulting tree, okay, will be 1 more than the height of the taller tree. We know that the taller tree had height log of the number of nodes that it contained. We're now adding 1 to know that this other tree that was the root had more nodes. So in some sense, if we add 1 to this, that's the same as taking the log of twice that. 1 to the logarithm is the same as doubling the size of what you were taking the logarithm to. Okay? This is true simply by the properties of logarithms. If I have something that's the log of this plus 1, this thing is the same as the log of 2 times the original argument. Okay? What do we know? This has to be less than the log of this plus this. Why? Because K1 was the size of the larger tree, the tree with more weight to it. So we know that twice the small has to be less than the small plus the big. Therefore, the height of this thing has to be less than or equal to the log of the total number of nodes, which is what we were trying to prove. So by induction, if we keep track of the height of the number of nodes in the tree, instead of the height, okay, this proves that we will never go wrong, because the height of the tree will always be order log n, okay, no matter what sequence of unions we do. Any questions? Okay, question.
That's it's probably going to give us an even better solution.
If we keep track of the height, that'll give us an even better solution. Now you're saying, then why did I bother talking about nodes counts at all and not just talk about height? Not so much because it's easier to prove. The real reason is because in general, maybe there's a better way to maintain our sets than just doing unions in the proper way. Okay. Schemes we saw before. One is, whenever you do a union, make sure you put the shorter tree on top. A second thing which we saw and we proved is if you always put the tree with the fewer number of nodes on top, that'll give you worst case log n. An even better scheme would realize that we're doing both unions and finds. Maybe whenever we do a find, if here is a tree, and we're going to be doing a find for, what's the root node associated with 4? What's the name of our tree going to be? 1. How are we going to find that? We're going to bop our way up to the root. How much time is that going to take? Well, log n, since that's the worst case time, but certainly time proportional to its height. We wanted. Since we've already spent the time finding our way there, why don't we go back and look at these links again? It takes time order h to walk there. Once we figure out who the root guy is, why don't we then go back and do the walk again? Only change all of these pointers that were not pointing directly to the root, change them to point to the root. Okay? If we, yeah, question?
Before you even know what the root is, you would have sort of
You would run into trouble. But what if you figure out who the root is? You go through here, you go bop, 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 root is 1. Let me go back and find myself again, and then walk over this thing a second time. And in the second pass, rearrange the pointers. Nobody would have gotten lost. Okay? If we do it this way, then the height of the tree would have gotten smaller. Okay? Why is that? Or potentially would have gotten smaller. Because all of these nodes, instead of being a distance of 3 from the root, now this guy's a distance of 1 from the root. And this guy, instead of being 2 from the root, now points directly to the root. Okay? So one other idea that we could use is whenever we rearrange the pointers that we have walked over, asymptotically it doesn't cost us anything to do this since we've walked over these pointers. Okay? So does everybody agree that this is a good heuristic? Okay, this is a good thing to do as far as general tree maintenance. Can hurt, okay, and potentially can help. Now if you do this kind of a heuristic, how would you keep track of the height of? Suppose, let's say, we now have a tree like this. It's a big, ugly tree. Okay? And you now do a find here. What are you going to do? You're going to move this node up to there, this node up to there, this node up to there. Has the height of your tree changed? Maybe, maybe not. Okay? It all depends upon whether there was another branch that achieved that height. And so keeping track of what the height of the tree is when you're doing these sort of path compressions becomes a sticky thing. You can't do that. Yes? Can I go through what?
No. Yeah, perfect.
Okay? So this is why we're going to keep track of the count of nodes. When we do a path compression, the node count doesn't change. The height may or may not. You can't maintain what the height actually is efficiently, okay, without looking at the whole tree if we're doing path compressions. So in fact, the really best way to data structure for doing this turns out to be where every time you do a union, you put the heavier node tree, the one with more nodes is the root, and whenever you do a find, you erase any pointers that you move everything up to the root that you encountered. If you do that, how much time can it take? Okay? Without doing any path compression, we showed that it took log n time, correct? If we do path compression, if we get better than log n, what can be better than log n per operation? Okay? Constant per operation. Turns out you don't get constant per operation. Turns out you do better than log n, but worse than constant. Turns out you get an analysis where you get a very, very funny function, something called the inverse Ackermann function, which is a function that grows very, very slowly, but still gets to infinity eventually.
Is it better or worse than log star?
It's better than log star. It's better than anything you could possibly hope for that's not a constant, because it does get to infinity. It's there very, very slowly. How slowly? The inverse Ackermann function of the number of atoms in the universe is 5. Okay? So it does get to infinity, but it gets there incredibly slowly. So this is one of the interesting things in the advanced analysis of algorithms, which I don't want to go through because the analysis is complicated. Okay? But it demonstrates that, and in fact, this is not a funny thing with the analysis. It's something that's really true. Path compression and merging the biggest. It will never take more than n alpha n time to do n operations. Okay? Which is more than a constant factor, but not by much.
Where n operations means
N means n either merges or unions. No matter any sequence of n merges and unions. Unions and finds.
Okay.
Will never take more than that much time.
But there have to be n finds in it also.
Well, finds it goes even faster. Okay? Because you have to do the finds in the union. Every time you do a union, you have to find. Oh, but you have to do a union. If you do a union of two vertices, how do you find that? What is the union? That's a good point.
Oh, okay, that's constant. Yeah, okay, fine.
What is the union? If I have two sets here, and I want to find the union of this and the union of that, what do I have to do first of all? I can't just link this point. What I have to do is to go back and find the parent. So the first thing I do before doing any union is a find.
Okay, yeah.
Okay, and that's where I do the cleanup.
Okay.
Okay, any questions about this? Okay, this really isn't that complicated. Okay, I can tell it may have been confusing. What's the important thing to see? If you do this union find data structure, you can always do these merges and these finds in log time, which means that you could maintain the the connected components from Kruskal's algorithm in log time each, which means that you can in fact implement Kruskal's algorithm in n log n time, m log n time. Okay, where m is the number of edges and n is the number of vertices. Okay, which is going to be better than Prim's algorithm for sparse graphs. Yeah. Okay, question.
Could you show that algorithm again, how we got to the...
How did we get to this thing? Okay. The basic idea of Kruskal's algorithm, sorry about that, this is bad, was we started out, we sorted all the edges, then for each edge, from maximum to minimum, for each edge, we found out what was the name of the component containing it, its first vertex, its name of its component in the second vertex. If these two were different names, it meant that they were in different connected components. If they were in different connected components, then we would add it to the tree. If not, we wouldn't. Okay? Once we added it, we now had to make these two components the same. That we did by doing a union operation. So the basic idea was find, union. If each find and each union took log n time at most, and we're doing m of them, one for each edge, that gave us an m log n algorithm. Okay? And that's faster than the n squared algorithm of Prim's for sparse graphs. Any questions? Okay? Anyway, this I'm afraid was a little bit confusing, but think about it, it's really not so bad. Okay? I give you a lot of stuff that's a lot worse, but I do a better job explaining it. Okay. Let me, okay, any questions? Sorry. Let me just spend a few minutes introducing the next topic, okay, which is finding shortest paths in graphs. Okay, where did my shortest path thing go? Oh. Okay, sorry. What is the... We've talked about spanning trees. Spanning trees provide a way to sort of measure how much length you need to sort of connect all the vertices. Another problem that comes up a lot in graphs is finding shortest paths. Okay? And it turns out that finding shortest paths will be very closely related to finding spanning trees. Okay? But although the algorithms are different in some crucial way. Why might you want to find the shortest path between two nodes in a graph? Well, one obvious application would be your graph was representing a road network. Okay? If you had a road network and the distances between two nodes were reflected by an edge of that weight, the shortest way to drive between here and Dubuque would be described by the shortest path in the graph, where each edge was weighted by the length of the drive time between two nodes. That should convince you that shortest path problems arise in practice. Okay? Came from a former student of mine who's now working for a video game company. Okay? He is working he wanted to model what he was working on a video game involving the Pink Panther. And the Pink Panther had to walk between locations. Maybe he was shooting at it. Okay, it was trying to get at, I don't know the details of it. Try to get to a particular location. And what they found was they needed a natural looking way for the Pink Panther in the room. Okay? And when they just had it walk in a random way, it didn't look like it was going anywhere. Okay, so what did they do? They programmed the space of the environment where the Pink Panther lived, okay, as a graph, had edges but distance between the graphs be corresponding to the distances of the points that they want to walk from. And then to get the panther from one place where he wanted to go to the other, they would have it follow the shortest path. And they found that the shortest path, since people tend to take the shortest path, looked very natural. Okay, and, so, and the panther looked like it was doing a good thing. Finally, there's other problems that come up, okay, in communications networks. Okay, let's say when you have a network, you want to figure out how long will it take for a signal to propagate across the network. Okay, well, the signal if it propagates, if you know the delay time between, okay, as being its weight. the shortest path along that network will correspond to the time it takes to propagate. Okay? Any questions? Next class, after break, we'll discuss algorithms for finding shortest path. Okay? So think about it, have a good break, and I'll talk to you guys later. Sorry.